So are you guys solving the H1 for this chapter? Properties of matter. Good. Yes.
Sir, not yet started.
Just a minute. Yeah, you're saying something?
Sir, yeah, HC1 more surface tension not yet started.
Okay. Okay. No, I'm saying that elasticity part, I think that we have done. No?
Yes, sir, that, yeah. Sorry.
So now surface tension is a very important topic from the point of view of marks in the JEE Mains examination. So very often this chapter is always asked one question in JEE Mains. So though it's a very small topic, but it's like weightage is very good. So if you know this chapter, at least one question is for sure you're going to do in competition. So we'll see like what kind of question we're going to solve here and what exactly is surface tension. So generally, we do not see surface. Let's say if you have a glass of water, you don't see the surface of water as a separate thing and the remaining water as separate thing. So what for us, the entire thing looks like one. So we don't differentiate between the surface and the remaining part. So in physics, if this is let's say the water level, let's say in a glass, and the water is filled up to certain height. What we don't understand that the entire water is not the same water in terms of some properties. So there is a difference in properties, and these are called energy based properties. And what is interesting that the surface is not exactly surface. So what we mean by surface is actually quite different from your perception. So what you call a surface itself is a volume. So in physics, the surface is defined as the first 5 to 10 atomic layers. So the first 5 to 10 atomic layers, because one atom is 1 angstrom. So this is roughly, if I take 10 angstrom, which is equals to the 1 nanometer thickness. So in reality, it is impossible for us to understand what exactly is surface because of the transparent nature of the liquid. What we see through it, and it is impossible to differentiate between the surface and the remaining part, and the remaining part we call bulk. This is called bulk, and this is called surface. So we do not differentiate between the surface and the bulk. For us, both are same. But in reality, they are quite different in terms of properties. Because only few atoms or molecules will be part of surface, the rest will be part of bulk. So who will be the part of surface? It depends on certain physical properties of atoms or molecules. So only few with certain characteristic can be part of surface. The rest has to be part of bulk. There is no option. But are these properties stationary? The answer is no. These properties are quite dynamic and they keep on changing very rapidly. So the particles in the surface keep on exchanging with the particle in the bulk. So every time new particles will be part of surface and the old will go back to bulk. But this process is dynamically balanced. So there is always someone in the surface. So it's not possible that we cannot have surface. It's impossible. But the question is how we decide that who will be part of surface and who will be part of bulk. So what are the criteria that we need to look for that will be deciding the two differentiation? So we'll see through some example. Let me draw this water once again. So let me change the surface. So imagine a molecule inside the bulk. Just imagine any molecule. So I'm just picking any random molecule. Now this random molecule is surrounded by other liquid molecule. So when I say molecule, then what do we mean by molecule? Just so let me talk about something called water molecule or liquid molecule. Or better will be liquid particle actually. So what is liquid particle? So in liquid, we do never talk about the atoms or the molecule, chemical molecules which they are composed of. A liquid particle is the smallest subsystem of atoms or molecules which constitutes the liquid. So it is like how many water molecule or let's say H2O molecule we must bring together to call it a liquid. So if let's say if I give you just only single H2 molecule, can we say this as liquid? The answer is no. Liquid is a phase, and phase is defined for the aggregate presence of molecule, not for the individual presence. So when we say gas, liquid, or solid, they are the aggregate behavior of molecules, not the individual molecule. So when we say liquid, then again we only talk about the aggregate behavior, and this aggregate behavior at least need certain number of molecules in a volume to be called a liquid. So liquid particle is the smallest volume you can imagine in which we have infinite number of molecules, the actual chemical molecules, and their cumulative presence is called liquid. So you cannot say one molecule as liquid, so unless they don't come in bundle actually. So this aggregate behavior of actual chemical molecules creates a liquid particle. So when we talk about liquid particle in physics, you can always think of something a tiny volume, and this tiniest volume may be like as small as a cube of millimeter cube. In fact, 1 millimeter cube Like if you draw 1 millimeter, 1 millimeter, 1 millimeter, length width and height will be same. Millimeter cube. So you can see the scale and you can understand how big is 1 millimeter, and you have to draw a cube of 1 millimeter in side length. So 1 millimeter cube roughly contains 10 to the power 20 atoms. So that is the size of the atom that you have to take one to occupy the 1 millimeter cube. You have to roughly take 10 to the power 20 molecules or atoms. So that is a tremendous quantity, and that many atoms or molecule constitute the smallest entity of matter that we call liquid or solid or gas. So when I say liquid particle, then it is a aggregate presence of a very large number of actual chemical molecules. Now we say liquid particle. So our behavior analysis will be based on the liquid particle level. We will never discuss the behavior at atomic or molecular level. So what we are going to study is the macroscopic behavior, not the micro behavior. So liquid particle is a macro part, and we will try to establish the analysis from this level onwards. So we're not going to discuss about the exact behavior at a very deep level. Okay. All right. So now coming back to this liquid particle. Now, if you look at this liquid particle, then this is also surrounded with a large number of liquid particle from all sides. So now this blue particle is just for the differentiation. Is surrounded with the from all sides by these red particles. You can imagine this way. Maybe I can introduce one more. So now between these pair of particles, they attract each other, and this attraction we call cohesive force. So we have something called and how we define the cohesive force? It is the attraction between the similar molecules. So we have two types of force. One is called the cohesive, which is between the similar molecules, and other is the adhesive force, which is between the two separate molecule of in nature. We have adhesive force, and it is the attraction between two dissimilar molecule. Okay. So we have coercive force and we have adhesive force, and try to understand this concept. So this blue molecule is going to be attracted by the red molecule, and this this attraction will pull the blue molecule like this. Let's say. So now because this molecule is pulled in all direction, and the pull force is symmetrical, and it is from three dimensionally. So it's from it is covered like a spherical ball. So what is the net force acting on the blue molecule or blue liquid particle? I could say. So the force acting on the blue particle is how much? Can we say zero?
Yes, sir.
So you can see that the net force acting on the blue particle is zero. It means it will, although part of the bulk, but it is not experiencing any net force. So it is as good as a free particle, just like a free gas molecule, and it can move through the medium freely. So that is the beauty of the liquid particle. It is free to move. So although the motion never takes place at a bulk level, like a big level, so the motion is always confined in a small volume only. So there is no like across the volume movement of the particle essentially remain at their same place. So they oscillate and they collide and they come back. So by virtue of collision, every molecule is locally confined in the entire volume, so no one is going to move far apart. Okay. But because of some uncertainty in the process, some of the molecule may move apart, which is always there. So the moment the same molecule will reach the surface, what will happen?
So there will be net force upwards.
There will need force downwards, because the downward we have bulk which is denser and surface is always a rarefied medium. So the number of molecules occupying on the top of the blue molecule is less and below is more actually. So the surface, I'll just do the two molecules to be enough. But the bottom will have so now here things will change. So we expect a less pull in from the surface side because of the rarefied medium, and we have more pull from the bottom side, and therefore the net force will be in which direction?
Downwards direction.
Downward direction. So what you can realize that it is difficult to be part of surface.
Surface.
So to be a part of surface, you need to actually overcome the net attractive force. So I can show it here first. So there is a net force acting downward, and any liquid particle who wants to be part of surface has to go against this net attractive force of the bulk to be part of the surface. And because you have to go against the force of attraction to be part of surface, so that requires some work done. And this work done gets stored in the form of potential energy of the surface. We call it surface energy. So every molecule which is trying to go from the bulk to the surface will have greater potential energy compared to the molecule in the bulk. So you can think that the surface is a high energy region actually compared to the bulk, and that is why this energy difference actually differentiate between the bulk and the surface concept in physics. So surface as a concept is a, you can say, location in which the molecules which reside there having high potential energy compared to the molecule which is within the bulk part, and they are not a permanent member of surface. So no molecule is permanent member of surface. This is like a continuous exchange. So we always have some molecule which is having high energy, and that goes to the surface, and the surface molecule with less energy will be part of the bulk. So the highest energy molecule will keep on replacing the lower energy molecule from the surface, and this dynamic movement maintain the surface all the time. So for us, these changes are not visible. So for us, everything is static, or we can say that for us, the surface is statically present object you can think of. So you can think the surface as a trampoline, which you generally see in the mall in which kids jump. So it's a thin sheet of trampoline with very high energy, a very high potential energy property, and this sheet is comprised of a large number of molecules, but these molecules keeps on replacing by each other, and that is how the dynamic maintenance is there. So you can think like they're, let's say, you're being supported by maybe 10%, and they are raising you using their hand, and next 10% is just below your body. So once they will remove their hand, the next 10 will support you again back. So for you, there is always 10 hands, but these hands are not the same. It is keep on replaced. So now to be part of surface, you can see it is really difficult because you need to overcome the attractive force, and therefore your energy is going to be larger. So now imagine the last case. What happens if the molecule reaches here? When I say reaches here means it is the topmost layer of the surface itself. So do we have nothing actually? There, the answer is no. We have air as a medium. So nothing is not the right word. So again, we have some adhesive force, some cohesive force. So molecule on the top, which is the gas or air, they will also attract these molecule. So attraction is there also, but I would say this is just only one. This is just a very rarefied medium, and then this force is even much bigger. So now the attraction is really stronger. So to leave the surface is a very difficult task. Why? So to leave the surface, you can understand clearly that this molecule has to fight a larger attraction force, isn't it? Are you guys realizing this? What is happening here? So now the net attractive force on this molecule is really large, isn't it?
Yes, sir.
And that is why this F net is basically bigger than F net part. And that is why it is very difficult for the molecule to leave the surface, because this attraction is really high. but it is not impossible to leave the surface. So if you have sufficient energy, you can be part of this, can be part of this air movement. And this process in physics we call evaporation. So evaporation is a process of leaving the surface by gaining sufficient energy from some external source. And that is why we also say that evaporation is a surface phenomenon. If you have heard in chemistry,
Yes, sir.
evaporation is a surface phenomenon. And because evaporation demands energy, so generally what they do, the blue molecule, while trying to leave the surface, will extract a lot of energy from the bulk itself or from the surface itself. And in the due process, when the molecule starts leaving the surface, they consume a lot of energy, which results into the lowering of temperature of the remaining system. So that is how we maintain the lesser temperature of water by keeping in a pitcher, because pitcher is made of soil or earthen potware, you can say. These earthen potwares are having an infinite number of capillaries, or you can say tiny holes, which you don't see. Through this tiny holes, the liquid will be absorbed, and then it will be later on evaporated by the surrounding. And in the due process, the energy of the bulk or the pitcher is consumed, and lesser the energy, we say lesser the temperature. So as the kinetic energy of molecule will decrease, temperature will fall down. This is what we know from KTG, right?
Yes, sir.
Temperature is the macroscopic name given to the some qualitative measurement of kinetic energy. So when we say temperature, we say for the aggregate presence of large number of molecules for the entire volume, and it is the indirect way of talking about the the energy part of the molecule. So through this discussion, what is clear that okay, we have come across various, I mean, process or phenomena, and this various process you can understand. So first is from the bulk to the surface movement, which is the first part, and the second is from surface to the atmosphere part, and that is how we define the surface. So surface is something not exactly same as the bulk, although we may not be able to distinguish by looking at it, but theoretically, or you can say in terms of concept of physics, surface represents a quite different object than the bulk. Okay, so still we haven't discussed about the surface tension. We'll come to that. What is surface tension? So what we have understood is what is surface so far, and once the concept of surface is clear, we can easily understand the surface tension part. Okay, so we can always assume the surface as some kind of trampoline, like just a minute. Okay, sorry guys. So I was taking my breakfast. Minute. So now we can see that the molecule is experiencing different level of attraction while passing through different boundary. So while crossing the bulk to the surface, there is attraction, and if you overcome it, of course, you will be part of the higher energy medium. And then crossing the surface to the atmosphere, even a more difficult task and which demands more energy. So only the highest energy molecule leave the surface and become part of atmosphere. This phenomena we call evaporation. And now you know why the evaporation is called the surface phenomena. So bigger the surface, more the rate of evaporation. So next we can go discuss. So now what you can realize that a system having a general tendency, what is a general tendency? To minimize the energy. So every system tends to minimize energy in order to gain stability, right?
Yes, sir.
So imagine if you take a smallest volume of liquid and if you put in a gravity free space. So if this is a some blob of liquid in a gravity free space, let's say there is no gravity, then this liquid is covered by the surface, and as we have discussed, the surface will have a greater energy than the bulk. So what is the way to minimize the energy? The only way to minimize the energy is to minimize the surface area, correct? So for every liquid, the only way to minimize the energy is to minimize the surface area, because surface area, bigger the surface area, more the high energy molecules will be present there. So to minimize energy by liquid, they tend to minimize their surface area. So for a given volume, which shape will have the least surface area?
Sphere.
Sphere. So for a given volume, sphere will have least surface area. Therefore, every liquid particle will assume a spherical shape in the absence of any external force.
That's where the water, like,
Yeah, that's why every drop is spherical. That's why raindrops are spherical. That's why every planet is spherical, because when we were part of the sun as a fireball, and when we got detached and we kept on cooling for many years, billion of years, then there was a liquid phase through which we passed, and while passing through the liquid phase, we become spherical. So spherical is the natural choice for any liquid, and that's why in nature we see always spherical things very commonly, like droplets, dew, and uh, everything else. Okay. So the surface area is the issue, and the only way to minimize the energy is to minimize the surface area. So this shrinking ability of a surface is the property of surface tension. So surface tension is the property by virtue which the body always tend to minimize the surface area. So what you can say? Surface tension is a property by virtue of which liquid will always tend to minimize its surface area. So this is the natural shrinking ability. So surface tension is a property by virtue of which liquid always tends to minimize its surface area. So that is a property. So this is the natural property. Now, like this is not something which we need to think about. So if we have a surface like this, this is the surface. You can imagine this is a thread. Now the thread will be, this is the natural way the thread is, you know, kept there. And now someone is trying to hang a mass from here. So once you do this, the rope will become like this. This thread will become like this, correct? And when you deform this thread like this, then the thread here will have some tension force, isn't it?
Yes, sir.
So the tension is only developed when you deform it, not when it is in a regular shape. So not when it is in the natural length. Only when you try to deform the length, it is developed. Similarly, every liquid will have a surface with the property there, but to experience the surface tension, you need to deform the surface. So imagine uh, this one. now you can, this looks like a visually, you can understand that this surface, so this liquid is there, and then you put some object, let's say you put a needle very gently. So if you put the needle very gently, then it will bend the surface. So the surface of the liquid is now bent. So by bending the surface, you do we increase the area or decrease the area? What do we do?
Increase the area.
We increase the area. So now the tendency of the surface is to minimize the area or maximize the area.
Minimize the area.
So now the only way to minimize is by going back to the original position, right? So the surface is like a now a stressed membrane. So surface, which you don't see here. Now the surface will behave as a stressed membrane. And its tendency is to go back. So what happens is that the object which you put, if I zoom this portion to demonstrate what is happening, let me zoom this out somewhere here. And let's see the two-dimensional view. So what we have is, let's say, like a disk. Okay. And the surface below is something like this. It gets dented here near the surface. And then again, while going away, it will become again flat. So generally there is a local dent. So what I have represented is exaggeration, but what we do is we create a local dent in the surface. So of course every surface is only locally deformed by the object which you keep there, and the surface molecule. Let me draw some molecules. So now these are like just I will for demonstration because these are the molecules, and these molecules will attract each other. So it's like it forms a support. So it will prevent the needle to go down by pulling each other. So they pull each other. So these molecules will attract each other. Now the last molecule which is in contact is pulled by the molecule on the right like this. So I'm doing this is surface, and this is also pulled towards this the last molecule. The rest will be the part of the system, and hence net force will be zero. So only the last end is what we consider, and these molecules will also split the force between themselves, and that will be net equals to zero. So now the tendency of the molecule is to actually stretch it back to the same shape as it was before, and this in turn will create the upward pull on the needle. You can see this. Now what I have shown is only one molecule pulling each other, but if you look at the length of the rod, then how many molecules we have? So we have infinitely large molecules, sitting here across the length,
Yes, sir.
on both sides, correct? And every molecule is doing the same job. So they are pulling across themselves along the surface. So there is a net tangential pull you can see parallel to the surface, and bigger the length of needle, more the pull force, isn't it? Can you see that? So as I
Yes, sir.
increase the length of the needle, the pull force will increase or decrease.
Increase.
which means the length really doesn't matter. So you can make as big as needle as possible. The surface will be supporting it across the length. So what eventually matters is the cross-sectional area, not the length, that you will realize later on when you will do some numeric. So now the idea is, because the pull force by the surface is acting across the length of the object, so as the length will increase, the pull force will increase. So we wanted to have something which is independent of this length thing. So mathematically, the way we define the surface tension is not a force actually, it is a force acting parallel to the surface per unit length actually. So surface tension is force upon length, it is not a force actually, because the length will grow, force will grow. So we wanted to define something which is property of surface, and properties are independent of dimension, and therefore we wanted something independent of the length, and therefore when you divide the force by length, what you get is a property, and this property we called surface tension.
So force is parallel to surface.
Yeah, force is parallel to surface always. So force is always tangential to the surface, and the tangent will be drawn near the surface wherever it is like having some curvature. So depending on the shape, the force will change. Understood? Is this part clear?
Yes, sir.
Okay. So the idea is simple. So let me define formally what is surface tension. So if we have a random surface of any random liquid, so let's say this is the liquid surface, and if I draw any imaginary line, so this is the random line which I have drawn, then the pull force by the surface will be acting normal to this line. This is the imaginary line actually, and this pull force is acting everywhere, and it will act on both sides of this line. And if I call this length as L of this imaginary line, then surface tension is defined exactly the force per unit length. So the net force acting per unit length is called surface tension. So what is surface tension force? So force is basically surface tension into length. So if you know the how much length you are touching the surface, multiply the surface tension property which is T by the length, you will get the force actually. So on this two-dimensional diagram, if I say the length of this needle is L, and if the surface tension property of the liquid is T, then I can say the force acting on the left side is TL, and on the right is also TL, because force is T times length of contact. So surface tension force is surface tension times length of contact. Understood? Is this clear? Is this clear, guys? Okay. So now this the imaginary line is there, and every point of the line is pulled by the surface. I mean molecule, and length will grow, force will grow. So what we define is surface tension as it is the force acting per unit length parallel to the free surface of a liquid. So force per unit length of the imaginary line drawn on the free surface of a liquid, like this. So we can put into proper wording where to put. Here only somewhere else of a definition. It is defined as the force acting per unit length of an imaginary line drawn on the free surface of liquid. So the free surface, when you dent it, then it shows the effect because the actual property is to minimize the surface area that we have discussed already, and therefore you will try to recover the dent which you have created. So you will tend to do so, and in the process you will apply force. So for example, in this case, if I talk about the FBD, so gravity will pull the needle by the force mg, and if I make some angle up to which it is touching, let's say this is theta, this is theta. So what is the net upward force? Can you find that force? I think this is easy to determine. So for equilibrium, what you can write here?
TL sin theta or 2 TL sin theta.
So for equilibrium, it is a 2TL sin theta, which is equals to mg, and so TL sin theta. So what is the maximum surface tension we can create? Maximum force. So maximum is only when it is almost semicircular shape. The dent is like a semicircular, correct? So the question is, what is the maximum mass we can balance by the surface tension? What is the m value which we can balance? So the maximum value of m that we can balance is m maximum will be how much?
2 TL
2TL
by
by,
G.
because sin the maximum value of sin theta is 1 when theta is 90 degree, which means when it is almost like this. That is the maximum case, and before that you will sometimes it will dent partially to. So the surface will keep on denting till it becomes semicircular, and beyond that it will sink. Now the object cannot be held back. So if you are balanced till that point, that's okay. After that, you will not be balanced and you will sink inside. And when you sink, then what you will experience is from the buoyant force. Okay. So buoyancy is when you go into the liquid, and surface tension is when you are just denting the surface, not going into the liquid. So for example, if you go to any lake, and if you the dry leaves falling from the tree floating on the water. So these dry leaves are floating in the water because of what reason? Surface tension or buoyant force. So when the dry leaves will fall on the surface of water, it is the surface tension which will hold them back. So it is not the buoyant force, but the boat will be floating because of the buoyant force for sure. So surface tension cannot hold the boat for sure. And if you can also see that if some insect is crawling on the water surface, you can actually see the dent also.
Yes, sir.
So you might have seen some big mosquito moving on a water surface, and they create a very nice dent which is visible in fact. And even during the flood, there is a, let's say, water in a river. The surface is just like a trampoline for these insects, so they can easily move from one place to the place unless it is not sunk by the liquid. So that is always there. Now this equation, or you can say this question, we can solve further. But before that, let me give you the dimension because that is also important. So surface tension, what is the dimension of surface tension? Dimension we can write as
kg per
ml square mlt minus 2, sorry, mlt minus 2 upon L. And L will cancel out. So what you get is the dimension of surface tension is ml0. So the unit is what? Newton per meter. Okay. So force is Newton and length is meter. So Newton per meter is the SI unit of surface tension. So now this is the unit of surface tension, Newton per meter, and dimension we can see ml0 t minus 2. Just remember this. So now we'll be doing a lot of questions. So the first question we just saw, that a needle question, and we realized something here that so let's say r is the radius, let's say this is theta, and now we have seen that the surface tension force is the surface tension multiplied with the length up to which it is acting. So that you need to think of where it is acting. And so if I say the density of this material is rho, which is the, let's say, iron, we are using iron needle. So you have written that 2TL sine theta equals to mg, and look at this hard to write. So 2TL sine theta equals to density into pi r square into length into g. And you can see that the L will cancel out. So no matter how big the length is, it really doesn't matter. So what radius of needle you can actually put on the water and it will balance it. So that is what we are trying to find. Rho pi. So R is under root of. So the maximum radius of needle that you can put on a water surface which will be balanced will be roughly 2T by rho pi rho g. That's a nice method. Pi rho g. Okay. And this you can find, and you will find that this will be in millimeter, fraction of millimeter. So I think the surface tension value is roughly 0.7 something. You can check the value of water, and you can substitute the value of density of iron and gravitational acceleration g, and you will realize that This will give you some fraction of millimeter in a diameter. So very thin needle, or lightweight needles you can put on water. So if the needle is thin in radius, you can put on water, it will be balanced. The length really doesn't matter. So it may be as big as you can think of, and if you put it gently over the surface, then it will remain there only without any sinking. So let's do something more. Like this was a needle problem. So you might have explained that if you try to throw some random mustard seeds on the water, many will sink, but many will also afloat on the surface. Have you seen that mustard seeds?
Yes, sir.
So these mustard seeds are really lightweight spheres. You can think that way, and the surface tension is a good enough force to hold them on the surface. So if you gently drop, it will not be sinking. Only if you throw inside the liquid, it will sink. So if you put every single mustard seed very gently without putting anything over it, it will only float over. Okay. So you can do with a variety of seeds which are very lightweight. So imagine the problem in which we have a mustard seed. So let me do this problem as. So now we are going to balance the mustard seeds, right? Balancing tiny spheres on surface. So now all these problems which you will also face in the examination, the problem is they will never mention a dimension, how big they are, how they look like. And these diagrams are individual. Individual means like your own visualization ability. Like you need to visualize the shape and you need to draw the proper ABD, then only you can solve the question. So imagine if I draw a tiny mustard seed. Now this is too small. No, this is the right size. No, this is the right size. Yeah, this is the perfect size. This is bad. So the whole idea is, can we draw the ABD of this size? The answer is no. So to draw the ABD, so to draw the ABD, we need to make it bigger, right? So we draw really big. So now this is the, I have zoomed the seed so that you can see it properly. And the liquid is not touching just like a circle, it is touching on this surface. This is a three-dimensional contact, right? Now this is something which you need to realize. So this is the center. So the real skill is in drawing the diagrams actually in this chapter. This is the radius of the, and let's say this is the radius r, small radius, and the liquid that we are touching. Let me do this first. So now No, we cannot show like this. I mean, this is not a right way because I should not put the T because this is not the two sides. We have actually like infinite direction, right? Everywhere. So that's you have to imagine. But if I say this angle as theta, if I call this as theta, this is also theta. So this will be 9 theta, right? So what is the net upward force? Can you tell me what is the net upward force? Anyone? What is the net upward force? So you can choose the small length dl. You can think that this is dl. So surface tension on this length will be how much? Tdl acting tangentially, right? And the net. Am I audible, guys? Hello, hello, hello.
Yes, sir.
So if you choose a small length dl on the periphery where the liquid is touching the sphere, the force will be tdl, right?
Yes, sir.
And this tdl will have component upward. How much? tdl sin theta. So the vertical component is tdl sin theta. So the net force is how much? Net upward force we can write as integration of tdl sin theta. But because t is fixed and sin theta is fixed, we can take it out. So what we have is dl. And if you add all dl, what we get is 2 pi r, correct?
Yes, sir.
Which is exactly the length of contact. So you can say that it is the answer is still the same. T into length of contact into sine component. So for equilibrium, what we can write? Fy equals to mg, which means T into 2 pi r into sine theta equals to m into g, and okay, whatever. And now this is the relation. Now you can also replace sine theta in terms of capital R and small r. So sine theta is basically r by r, which is a very common way of converting sine theta into r by r. And this gives some relation, nice relation. So okay, whatever. So what is the biggest radius of the seed that we can balance? So the capital R is 2 pi t r square by m. And we know that the maximum is when r is capital R, because this r we can grow up to capital R. So r max is how much? So r max is, for r max, the r equals to r, both will be same, no? And so you can solve this as,
Mg by
and you can see the r max actually comes out to be mg by 2 pi. So given a mass m and everything else, so the r must be having this value, then only it can be balanced. Otherwise, we cannot balance. So a bigger radius will sink easily. I mean, if it is having mass and the size ratio in different proportion. So surface tension, I mean, you have to solve questions like this only. So you have to think a lot. Let's say next problem is very famous. So now this is a ring which is kept on a liquid surface, and you can see as you try to pull it out of the liquid, so it is initially there's a sunk, and now you're trying to pull it outside. You see something like this. So liquid will bend near the surface, isn't it? You might have seen this. You might have experienced. If you try to pull it, so let's say I'm trying to pull this.
Yes, sir.
So to pull this ring out of the liquid, what is the minimum force that we need to apply? So to pull the ring out of liquid, find the F minimum and the radius of the ring, let's say R. And the mass of the ring is, you can see, capital M, small m. So now you need to realize that when you try to pull it out, so if you look at any cross-sectional view of this ring, don't see the entire thing, just look at the cross-section. Because it is coming out of the liquid, so initially it was completely filled. So the maximum surface tension will be when it is liquid is pulling this way from inside and from outside. You can see it will pull like this. So if we if I say this is the DL length, then the surface tension will pull downward, and with what force? TDL from both sides, correct? And then the net downward force we have to add all across all lengths. So the net downward force is how much? F downward is how much? So it is TDL 2TDL integration over the length to integrate over the ring, and the DL integration is what? 2 pi r. Understood? So the inner ring radius and outer ring radius are same because this ring is thin, not a thick ring. So the maximum downward force is how much possible? It is 4 pi RT. And apart from this, it will also have a pull force downward because of gravity. We can say DMG or lambda DLG. So the net downward force will be this plus, and this will be basically mg only, just to write. So the minimum force required to pull will be how much? So the Fy minimum that we need to pull this out of the water is 4 pi RT plus the mg. Okay. So instead of a ring, if I give you a disc, then what will happen? Yes, tell me. Hello.
So why did you took 2DL, 2TDL?
Because you are touching from the outer surface and inner surface also, no? The water, how water will touch? So water will touch like this, and this part is inner, no? This is outer. So the liquid is also touching here, which you don't realize. This diagram doesn't look good, so I haven't drawn this part. Clear?
Sir, then in the previous problem,
You can touch only one surface, outer surface.
oh, understood. Yeah.
Imagine some a tube, right? A tube will have inner radius, outer radius, and the liquid will touch the right outer surface and inner surface both at the same time. And because it's a thin ring, so the radius will not change. If it is thick, then radius will change. So, for
Yes, sir.
example, if I draw something like this, if I draw something really thick, okay. So this is really thick. I mean, you can see the radius is having difference, and okay, how to do this? Yeah, so you can just imagine it's a tube actually. So how you can do a tube? Mm, no, you can just imagine tube. So this is and if we try to pull this out of a liquid, then the water will touch here,
Yes, sir.
but here it will also touch here, no? Understood.
Yes, sir.
And both touch will be different. So what you need to do is you only consider one cross-sectional view to solve the question. Don't look at the entire thing. That will confuse. So if you look at the cross-sectional view, this side will have the force, this edge. So if I cut theta and d theta, if this is d theta, then the length, outer length is not same as inner length. You can see it's r1 theta, this is r2 theta. Understood? So theta is same, but because the radius will change, so this will be having this outer will have experience the force T into R2 d theta in this one. Is this clear?
Yes, sir.
Apart from the gravity, this is you are trying to pull this, and then it will have some mass also, which you can write as dmg, and this is the dfy. So net force will be how much? Integration of all this will give you 2 pi r1 plus r2 into t plus mg. That's it, isn't it? It is difficult to understand.
Understood, sir.
So you can do it for any shape. Let's say if I draw a square frame made of a wire, a thin wire. So if it is a square frame made of a thin wire of length L, so what is the net force required to pull this out of water? Just tell me the answer. So however thin the wire may be, it will have cross sectional area, right? So liquid will touch on the two sides. the inner side and the outer side. So how much Fy we need? Tell me, guys.
Sir, 40L plus NG.
40L is only one surface, na, one length. So outer is 40L, inner is also 40L. So net is 8TL. Na? See, wire is a cylindrical shape, na? So however thin a wire may be, it will have some cylindrical shape like this. Hmm?
Last.
So the surface is like both sides, na? There are two sides actually.
Yes.
So it is going to be how much? 8TL
8.
plus M. Is this clear?
Yes, sir.
See, this chapter is all about your own imagination. I mean, the diagrams will not be as clear as you may expect from the examiner. So they give a very simple diagram, and then you have to figure out what the actual diagram that you need to draw to get the answer. Okay. So you must have seen the liquid dropper, eh? Have you seen?
Yes, sir.
Yes.
Like eyedropper and all. So, or any liquid dropper, not eye, just any. So if you try to push the liquid dropper, I mean the the top of it, whatever you what you call it, like a small pump. So they give the small pump, air pump, which you press and liquid is disposed out of the tube. But in the very beginning, you can see the liquid will create a droplet before it gets detached. So let me draw the actual liquid dropper. Now near the bottom, the cross-sectional area, they make it very small, right? So opening is a small area. and then you fill the liquid up to some level. Okay. So now when you try to press this, it will create a droplet at the tip. Okay. And let's say the droplet is almost spherical because the top is very small cross section. So then only after certain radius this will detach because of gravity. So let's say I'm saying that this will be detaching because of gravity. So let's say the droplet gets detached. Spelling you can check detached due to gravity. Then find the maximum. This is, let's say, capital R, because the radius of the opening, this radius is smaller. Find the maximum radius of droplet released given the radius of opening is smaller, and surface density. So you can try this out then also. So if you can draw the proper diagram of the sphere, then you will be getting the answer. Else it's impossible. So try this out. Density. Take the density of the liquid is rho. Sorry, I forgot to mention this. Density of liquid you can take as rho. And it is getting detached because of the gravity only. So surface tension is trying to hold it back and gravity is pulling it. So when they are balancing each other, it will fall down.
Hello, sir.
Yeah, tell me.
Sir, I got R max is equal to under root RT
Hmm.
by 2 rho G.
Hmm. Okay. And the root is correct, I think. Let me check. So if you draw this diagram, let me draw this separate. It is like, let me remove the part of it for the sake of clarity. This is the opening part, right? And this radius is given as R. This is the capital R and this is the R. So we know that surface tension will act along the tangent, right? So the way it is going to act is this way only, along the tangent. And it will act everywhere. So I'm just doing the two corner cases. So it is acting from all sides. So if we take this angle as theta, so if you take the TDL cos theta, this is theta, this is 90 theta, this is theta. So you can see the TDL cos theta into, I mean, integration, which is like T cos theta into 2 pi r. So this you can say T cos theta into 2 pi. Length of contact is how much? 2 pi r.
Yes, sir.
And this must equals to weight of the liquid, which will take almost a spherical. So rho into 4 by 3 pi r. No, pi r. Why we are taking? Because we are assuming this is almost spherical and into g. Yeah. So 2 pi will cancel out something like this. So T into cos theta is r by r into r is 2 by 3 rho r cube g. So r power 4 is how much? 3t r square by 2 rho g. So the maximum radius you can have is this only. So this is the JE mains problem. Is this clear?
So my equation was right, but after that,
Pardon?
so I got the same equation. T cos
Hmm.
theta to pi.
Okay. But in this case, you cannot replace theta by 1. So you cannot say cos theta is 1 because here the theta is in a way fixed. So you cannot change this angle. Okay. So the only r is constant quantity. So as capital R will change, theta will change. So cos theta is always r by r only. Okay.
Yes, sir.
So we can do the next question. So this is everyone's favorite time pass that we all have done in the childhood. Creating the soap bubble, right?
Yes, sir.
So to create soap bubble, what you do is you take a ring, you dip into the soap solution, hmm, and through this ring you used to blow the air, right? So this will have a thin film. This will have a thin film, and if you blow air, then this will actually blow as a liquid. I mean, it blow as a soap film actually. You can imagine this will blow like this. I should never remove this part, but okay. I'll just do this by freehand. So the question is, this is a really bad diagram. So thin one. So depending upon how fast you blow, let's say this is the velocity of the air is v. So this will go and hit the back part of the sphere. And if you have remember that this force will try to push the so bubble as big as possible. So to create a big bubble size, we used to blow slowly, right? If you remember, because if you blow really fast, it will is become a small bubble and leave the surface. So now across the world, there are many competitions in which you have to make the as big bubble as possible. There is a competition across the world. So this radius we can take as r. Let's say radius is b, velocity is v, and the same question: what is the maximum radius we can create? That's the question. So if you remember the thrust force, how much is thrust force formula? We have done in the which chapter? Center mass, variable mass concept. So thrust force of the air will be how much? Let's say density of air is rho. So you don't remember, it is rho cross-sectional area into v square. So the thrust due to the air will be rho pi b square v square. Okay. And now you are supposed to find the radius of the soap film. Now this is the soap film, and what the problem with the soap film is, soap film will have double layer actually. You know double layer, inner and outer, and these two layers are almost touching each other, but there is a micrometer gap. Now this micrometer is really small, and because of the double surface, you need to actually assume double surface tension, not only one, the inner and outer. So that is the only difference. You have to just make the surface tension force double. So this is same as the previous problem. The only difference is earlier the gravity was pulling, and now the thrust force will be pulling it off the ring, and rest is same. So can you try this question? Is this question clear? Try this out.
Hello, sir.
Yeah, tell me.
So is it 40 by rho AB square?
Very good. I think that's correct answer. So it is similar to the previous case. It will become t something like cos theta. Now why he is coming? Atharvadesh Pandey. Okay, why you are joining right now? Tell me. Hmm? This is the class ending time, so you are joining right now. So you can leave this class. Go ahead. Don't attend the class. Leave the class right now. Either you leave or I will remove it. Do it gracefully. Attend from the next lecture. So here the t into 2 pi b and a similar thing. So if you do the FBD kind of thing, so surface tension is always normal to this line. Okay. You can just do, you can just do in separate line. I mean, I can just do a separate triangle. That's always easy to draw. So opening is, this is opening, B radius. This is the capital radius of the bubble. Okay. You can draw like this. And the surface tension is always tangential, so it is always perpendicular to R vector. And this time this will be t into 2 pi r, or we will say t dl. You can change this way at a point. And if I say this is theta, this is also theta. So you can clearly see that net force will be forward force because the vertical will cancel out. So t dl sin theta, and if you integrate over the perimeter, you will get t sin theta into 2 pi b. Sorry, and this is equals to rho into pi b square into b square. And the sin theta is b by r. You can see. So pi b square will cancel out. You can see from here. And because it's a double, yeah. So I have to mention this is 2 times because it's so bubble. So 4t by r is rho v square. So the radius of the bubble that you can create is 4t by rho v square. And that clearly says that if you blow very fast, if v is really high, r is very small. So you will see a small droplet. So to create a bigger droplet, you have to blow the soap bubble slowly, like a gentle push will create a bigger bubble. So next time when you're doing the same, you can practice this and you will realize that okay, this formula really works. Okay. So so we are done with the variety of problem of surface tension. So imagine if I give you a ice cube, and if that ice cube is converted into liquid at 0 degrees Celsius. So after becoming the liquid in a gravity-free space, what will be the shape of the ice cube? So will it remain cubical shape or some other shape?
So sphere.
Yeah, correct. So once it will melt into liquid, it will quickly become spherical in shape because surface tension will try to minimize the surface area. Okay. So I hope this is clear.
Yes, sir.
Okay. Uh, let's see if something is left out. So okay, we have again a similar problem, and this is the last problem. So if you try to boil water in any vessel, so you will experience something. So while boiling the water, you can see uh, a large number of tiny droplets are sticking to the wall of the vessel,
Yes, sir.
and close to boiling, when they're about to boil, then all starts leaving the surface. So at boiling, the drops will start leaving the surface. So the question is, if I take the liquid in a container, and if I consider small droplets, so these are really small, but for the sake of drawing, I'm drawing it bigger, as you can understand why. And this is basically a hollow. This is a hollow one. Okay. So of course it is not empty, it is filled with air, and let's say this is air. So that you can understand this is same as here. So now this air bubble, okay, so now here I need to give one extra concept. So this air bubble will grow in radius. Why? Because as the heating will happen, then the gas will expand, and as the gas will expand, this bubble will grow in size.
Yes, sir.
So now what happens? This bubble will is because it's part of the liquid, so they experience buoyant force actually. So this buoyant force we write as volume of the object, like which is displacing the liquid. So volume displaced by the liquid into rho into g. This is almost spherical, and the part they are touching is very small, so that you can always ignore. So this radius that they are touching is r, and r is much bigger, much smaller than capital R. So this r is very small compared to. the R of the bubble itself. So question is, if the detachment of the bubble is due to buoyancy, then at what radius it will detach? So if the air bubble, we call it air bubble, not droplet, we call it air bubble, detaches from surface only due to buoyancy, then find the radius of bubble. So again, typically you have to do the same process, and the only force you have to apply is bond force instead of other forces. So in different situation, the reason of detachment will keep on changing, but anyway, that's easy.
So point force of force.
Hmm? Buoyant force will act upward, yes, definitely.
Sir, hello, sir.
Yes, yes.
Sir, is it 2 pi r square t by v rho g?
Let me check. So it is again similar thing. It's a 2 pi small r into t into r by capital R equals to 4 by 3 pi r cube v rho g. So this is the equation. And what we're looking for is r. Hmm? So same answer. I think r power 4 is sorry, 3 r square t by 2 rho g. So this is similar to the very first question that we solved. Again, this was J mains problem. So every question that we have solved is basically already previous year J problem. And because surface tension is the toughest topic in J mains in terms of difficulty level, because these questions are better than J problems. So you need to practice a lot and get a command over these kind of problems. Although I have solved all problems, but I will again suggest just practice these problems again and again to get the hang of what we are doing exactly. So the next lecture I will start the surface energy part, and it will continue for maybe one lecture, two lecture. Hopefully next lecture we should be able to almost complete, if not all, and then we start the viscosity.
Sir, I was
Sir,
confused because that R is very small than capital R, so that term will be zero. So I think, yeah.
If you make everything zero, then what will happen? Nothing. Here the idea is to assume this to be a sphere. We assume small r is smaller than capital R, so that we can add volume formula as 4 by 3 pi r cube. If you take as a partial sphere, then the volume is difficult to write, isn't it?
yes, sir.
And
Sir, I heard that E is.
yeah. Hmm. So this is the exact reason, like why when the water is about to boil, why the droplets start leaving the surface, because the gas expands to the extent that where the bond force is good enough to detach it. So you can see that small things in our life can be explained by the laws of physics and simple mathematical relationship as well. So that is the beauty of physics. You always discover the real life events in a mathematical way, and that is very satisfying for any curious mind. So I hope you have learned something real life. Bye guys.
Bye.